Get started. As more people are coming, I'll say that, but I think we'll get started. How's everybody doing on Monday, June the 5th? Good. Awesome. All right, cool. So when the video will start. So yeah, today's paper was one that I think in previous conversations in the reading group, people have been a little bit like, sometimes, what are some foundations of specific stuff? And, one thing I looked at was like survey papers. I actually am a big fan of survey papers, even though there's not many conferences that accept them or care too much about the analysis. There's like one big one, ACM computing surveys, but I think that's even by not even every year. But this one was pretty interesting. So we have a taxonomy on job scheduling on distributed computing systems, 2015, 2016-ish. Does anybody want to do a little bit of a 5-minute spiel on like the kind of high level of the paper? Any volunteers for the taking? Oh, come on.
I can do a high-level overview summary.
Cool.
So,
go for it.
May I share a screen? Just so I can share
yes.
the paper as well.
Yes, for sure.
I would be scrolling quite a bit.
Cool. And I think, let me know if you don't have access. I can make sure.
I do not.
Get it going. All right, let me do that. It should be.
I got
now.
Cool. So, as already mentioned, this is the taxonomy of job scheduling on distributed computing systems. So they are, in the immediate sense, introducing terms to classify all of these different problems we see, because there's, broadly speaking, not a good consensus on what the terms mean. And then they actually take those terms and try to apply that to both classify problems that they find, problems through papers that they search for, and then further, they define a taxonomy for solution spaces and they classify the problem's solutions as well. So I mentioned that this is actually probably one of the quotes mentioned. So at the very minimum, we wish that all papers about job schedulers make clear their assumptions about the workload, the permissible actions, and the metric that is being optimized, which is very interesting because there are a lot of solutions, and I wanted to start getting to that space. They explain a lot of their rationale as well as a background. So a lot of these taxonomies are broken into 3 groups: the workload group, a set of features. So every problem essentially has a workload, resources, and requirements, but what sort of workload they want, what sort of resources they want, what sort of requirements they have are all going to differ. And they start to define all of those features lower. But broadly, the goal is to optimize a goal subject to static workload features, static requirement features, and the requirements that we define at the onset. So I'm going to scroll past this just to show this particular figure because it's defines the majority of it, just at least a high level, where you have types of workloads. So the different sources, whether it's a single user with a single job, a single user with multiple jobs, different job structures, single task, just it's trying to accomplish a single thing and it's done, to independent heterogeneous tasks. It's accomplishing a lot of tasks that are unrelated in many ways. And broadly, all the way down to a real time, whether it's no real time or it's hard real time. So those are all the different types of features that they define, at least for this, as well as resources, things such as whether or not your resources are all effectively equivalent to each other and can be treated as the same foundational unit, or whether you're going to have different servers, for example, what sort of scaling is available, whether you have to, for example, manually put together a instance or just acquire another VM. What sort of sharing is allowed on the resources, whether it's completely dedicated metal to OS, even mentioning geographical coverage and federation. And then, of course, the requirements. I wanted to mostly point a lot of this because this is very much the bulk of it. They later on apply these, but this is very much just how they start to say we can start looking at and classifying all these different problems. So I wanted to scroll past that as well. Then they define essentially, this defines what sort of problems, like, or not, sorry, not what sort of problems. This defines what sort of workload we have, what sort of resources we have, and what sort of requirements we have, but it doesn't define how we actually try to solve it. And I mentioned that because that's where they start getting into their scheduling requirements. No, sorry. That's where they start getting to their scheduling solutions. I also wanted to mention this before we get too far beyond it. They define a metric essentially to compare two scheduling problems. And effectively, it is the number of features that are shared in the workspace, in the resources, and in the requirements. And essentially, you have a 1 if it's shared feature, and it's a 0 if the feature isn't shared, and then you just sum over all of those. So if they're exactly the same in feature set, you end up with a 1 for this metric, and the more dissimilar they are, the closer to 0 it is. And they use that to start comparing different problems. So that's an important aspect of it. When they do a lot of this comparison, that's what they base it off of. I want to wrap up because I'm taking quite a bit of time to get this 5-minute summary, but I wanted to close, I think, on the scheduling solutions, which is they define it in this sort of, I don't think I'm in the right part. Here we go. They define it in a few key ways of sort of whether it's defining it with an optimal, what sort of operation is allowed, what sort of topology distribution is available, which tiers down, as you can see, because if you have a distributed topology, is it centralized or decentralized? And then how are those being managed? And then from here, they really start breaking into the actual statistics of it. So they use all those definitions to start classifying papers, how similar they are, and talk about the number of citations and how we could be reusing a lot more of this work. I'm going to, I think, call that my summary of this.
So that was a great summary, by the way. I just want to say, really awesome. Thank you, Eleanor. Yeah, I mean, I think you hit on the right points and all the important things. There's a lot of great reference pieces here. I think even in 2023 is what we're in, right? You won't probably get something so detailed in terms of all the mechanics they kind of show, all the different variations. Obviously, I think of an era, they talk a lot about the movement from grid computing to what we know more as cloud computing and other things, which I think is really interesting. It's like, oh yeah, grid computing was kind of a thing. I don't hear about it much anymore, though it definitely exists. But that was also another kind of tidbit from the kind of historical viewpoint. That's really good. I mean, I have some personal things that I think are cool in this paper, but I want to kind of open it up to people who want to kind of go off their thoughts or like expectations kind of going into the paper, or even just reading the abstract into what maybe the paper is actually about. Does anybody kind of want to kind of convey that, or is there anything that kind of kindled interest? Is anybody working in something similar, like in working with like distributed algorithms? Obviously, I think a lot of people use systems that provide these mechanics under the hood, but I'll leave it up for people to have thoughts on that.
Can I actually ask a couple of follow-up questions based off of
Sure.
that overview? So going back to section 2, one of the main points is optimize Q.goal, subject to static features of W, static features of R, and requirements of Q. And then kind of looking ahead to that tree breakdown that we get later. I think it's like in section 3 where it starts the taxonomy. So I'm curious about like if I'm thinking about this as like I've got all of the scheduling systems that I could possibly have. I'm just putting them somewhere, and I'm trying to make a mapping from, okay, this basket of R, W, and Q, and sets of those over to specific implementations. I think that's what this survey is generally trying to do. It's like painting a picture that this mapping exists. And I'm trying to understand the relatedness of those different kind of input. I don't know what to call them, input like parameters, input features that we want out of our system, and understand which ones are mutually exclusive versus which ones can, like you can have a set of like, yeah, maybe you can have W3.1 rigid job flexibility, and also you can have single user, single job. Like which ones are mutually exclusive, which ones are not necessarily mutually exclusive.
Yeah, I think they do handle this, though maybe not as specific at all the feature level, like they kind of showcased earlier to later. But I feel like these groups of problems kind of dictate that. And I admitting read these pretty quick, but you know, I thought these actually get at essentially what you're going for, and someone else can come in if they think that there's something somewhere else. But I think they try with these groupings here to kind of cluster for what are the kinds of things that are related. So here's like failure and data locality, where like, for example, data locality doesn't come into place in a lot of the other groupings. And they talk about that, right? Because it's one of the few papers that actually calls out data locality very specifically. And also like here, scheduling a workflow job with homogeneous shared cluster. So, I mean, these are probably not all the groupings that were possible, but and obviously they're baking this in with the related work. But I do think this is where they're trying to get at, like these are map reduced type of jobs. These are Hadoop kind of jobs. These are grid kind of jobs, or quality of service kind of jobs. So I think this is where they're trying to do that. Does anyone else want to kind of chime in there? Maybe, but they didn't like show the graph. Maybe like, you know, I mean, you get a little bit of like where these like these large ones for each group, right? Where they try to basically say, here's the frequency of these kinds of things, right? I don't know if anyone else wants to kind of chime in on that answer, but I think this is the attempt to do it. Obviously, it's a lot of data to read through. Yeah, I mean, I felt like that's what they were covered. Like, are there other groups that are kind of missing or not conveyed in certain things? But I think this is kind of these tables are essentially setting it up and like probably looking at frequencies that are pretty high. Like for example, right, this is the single task heterogeneous dedicated clusters. So you're going to get, you know, non-federated, these kind of things that show up in terms of values. Like you're not going to get soft real time, for example, stuff like that, which I thought was pretty interesting, where these things kind of showcase more. I think, what is it, like one of the ones they call out is like SLA and SLO aware, which actually most jobs 2016 were not. I wonder if that's actually changed now. But you see here, for example, so quality of service driven stuff, you get the 100% SLO aware. Yeah, that's a great answer, Eleanor. I don't think the features are necessarily mutually exclusive. I think there are solutions that probably have to support, right? And when you see some of these, I think you're looking at for job structure, job flexibility, these low percentages. There's always some trade-off or some use case that might have to deal with that. Marc-Antoine?
What I find fascinating is in this group, we worry a lot about how much do we need to coordinate work, right? I mean, we love CRDTs because no coordination required, and so many types of problems require sequencing, coordination. And I see nothing about the coordination dynamics in this paper, which okay, it's a choice, but I do find it surprising because for me, it would be a key aspect. Like I was looking push-pull. Okay, what about back pressure? These are things I'd really like and expect to see. And again, for certain tasks. So I was surprised.
So I would say
how little role it plays there.
Yeah. No, I think that's great. I want to call it. I feel like, and this is just more going on the specifics of it. And of course, they're tackling a very specific paper here. I think in some ways, coordination is a different survey paper. And that coordination and scheduling are actually separate processes, right? Scheduling is like, at least, and we look at this actually in some of the work we're doing at Fission with IPVM, which is the execution of something. And when you're going to say like, what is a graph and how it will execute, is scheduling. And coordination is the piece where you determine, and that's like a different, it's probably like 150, whatever, 1,000 papers we can go through. I mean, maybe that survey exists. I haven't actually, but I do think they talk a little bit about sharing and stuff here, but I do think it's almost probably a different, it's all about runtime and distribution, but they're probably different, different realms a little bit.
Really, my question is, how well can those two aspects be detached? I mean, it seems to me that issues of interdependence would impact the job structure and things like that. Now, of course, they can just take it for granted that assuming we have interdependency and it's the coordination's part of the job in a way, we can abstract that out. But I wonder how well it can be abstracted out. That's really my question.
No, it's a great point, because, for example, if we're talking about things like data locality, right? So moving data closer to do things, that's obviously a way that you can coordinate how you're then going to execute something. So you're 100% in thinking about this, right? Or do you just run jobs where you're like, I'm going to run it on 3 different machines and whoever wins, wins. And I just go for it that way, right? That, it's another characteristic, right? So that's a great point. Anyone else kind of want to chime in on that? Because I do think it's something we've been thinking about a lot. But I want to see if other people have thoughts on that. Because the one thing I'll say is, just on scheduling, looking at all these features, I said someone trying to build a distributed runtime, there's a lot of things to think about, right? And that's without even all these things about coordination. How do you get the data in one place? Who should run it? I mean, we talk a lot at Fission about capabilities. There's the capability of like, can you run it? If you think about it in off cases, identity cases, do you have enough resources to run this thing? You imagine now with all the jobs we can run with large AI modeling, with graphics and these things. I mean, NVIDIA is releasing crazy new cards every day, and we want to allow these kinds of jobs, right? How do we kind of coordinate for that, and and run? I think to this paper's point, how do you run very flexible sets of workflows and jobs, right? So this is super tough but interesting stuff, and has a long history. But to this paper's point, not really, people don't really go back to it. And of course, to your point again, Mark, as well, like, yeah, I think the coordination of like, how do you merge data, how do you move data? The paper we did last month, which is really like a couple weeks ago, on the Ambrosia paper, hides some things, but when I know pretty well from like in the Microsoft system, they don't, they have systems like Orleans and stuff, right, which can actually activate certain grains of data based on use cases, and if like the same data is being used over and over again, we'll kind of simply hot cache those in certain locations, right? So there's a lot to think about in that kind of merging of environments of executing things. Anyone want to kind of go off on that point? I'll open it up. All right. I think everyone's just saying you're right, Mark Antoine. But yeah, I bet there is probably another survey paper we can find that takes essentially, I would say with the stuff we're doing at Fission, for example, though really it's all about distributed scheduling. To your point, we've actually like separated out what is like coordination from execution scheduling, from to also like having something like an agent that's also just like there to forward information, right? So there's a sidecar.
So you've managed to abstract it, so that's actually an answer.
Yeah, and it's the way we've thought about it, right? But I think terms wise, you can call the whole thing distributed scheduling. and yet coordination is not here. So it's the levels versus the expansion, I think, for sure. Did anyone, I mean, I don't know if people who have backgrounds in this stuff, because I actually felt this paper was really helpful to me, again, working on some of the stuff too. I think someone mentioned in the Ambrosia paper, there's a lot of terms, we spoke last time about virtual resiliency, and in these kind of aspects of terms. And like someone I think mentioned, someone who's on this call, where can we get more terms? Where can we get things defined? And did having these definitions in this paper help out at all for anybody here?
And when you say terms, are you referring to the breakout of the static enumeration of all the different input parameters from problem space into solution space?
Yeah, exactly. Yeah.
And I guess that's probably what you were saying about in the beginning, the fact that people don't cite a lot of these papers is probably evidence that there's not a whole lot of awareness about what the total, I guess, like input parameter space looks like, because it's hard to discover.
Right. It takes, essentially a group of researchers to make something their PhD or master's, I don't know if there's a master's thesis or not, to do the work of going through 1,000 papers. Yeah, exactly. Yeah.
Maybe a little bit of a meta question. Can you guys maybe help me understand section 6.1 a little better? So that's where it talked about how to group, I guess, related problems to their solutions. So I'm trying to understand what's going on here. So we've got a really so in abstract, if I squint, we've got like a really highly dimensioned input parameter space of different, I guess, ways that we can categorize the system. And an interesting point to this, they're talking about using a distance metric. So I've been kind of trying to play around with this technique a little bit, just loosely. Being able to take these these taxonomy trees, which divide up, hey, you've got an input parameter space, and bind it into a metric space, which has literal. So you've got some complicated output space, which is even higher dimensioned with this signal. Sorry if I'm being super hand wavy, but the state signals are super messy, and you're trying to create some abstraction, which is there is a more tight causal mapping of movement in your input parameter space to this craziness, this chaos that's going around in the output parameter space that this paints onto, that this images onto. And understanding, so that they use the word using the metric. And I know in particular, there's this thing called when you use a metric in a metric space, you're effectively saying, can you define the distance and there's some relatedness function to evaluate trade-offs? And I'm kind of curious about that in terms of understanding baskets of related features. So is this saying how can I better understand that the relatedness of different, if you go back to the taxonomy tree real quick, maybe I can just illustrate something that I might be looking for. Yeah, so how can I evaluate rigid, moldable, malleable, evolving, something like that for job flexibility? Is there a way to score each one of those dimensions in a way where I can be hey, this thing has 5 different orthogonal features, but they have some relatedness function, and I can evaluate hey, here's the trade-off function between rigidness and malleability, or something like that.
Please.
I'd love to answer. So the first thing I'd want to say is that when you are discussing a metric, no point necessarily has a distance in of itself. So this is always comparing 2 different things. So the way that they define the metric in this paper is, for example, 2 problem sets are similar if they share a feature and dissimilar if they don't share a feature. So if we have a problem set where one has rigid W31 and the other one has moldable but not rigid, then you actually end up having to add both of those differences. So you add 2 to this metric. And it's scaled, so it's not literally 2, but that's what is happening. But if you have 2 problem sets and they both have rigid, then that difference is 0, and you can say that these are like each other. Does that make sense as far as like the metric part and how these 2 things are similar or dissimilar?
Yeah, I think that does make sense. And this survey, I guess, is just looking at like problem solution fitness as just being like a simple division problem of number of satisfied constraints versus possible.
It's a cardinality, really, right? Yeah.
And they use what's called an indicator function sometimes, depending on what field you're in. And it's called an indicator function because it's 1 if these 2 things match, and it's 0 otherwise. And I guess it's a little different because it's actually shared features, but still. As far as the clustering these, what they essentially do is they will, and I didn't read to know if they necessarily did it the way I'm about to describe, but the general idea at least is you find some sort of point in this space, so some sort of combination of features from this problem set, and then you essentially find all of the things that are within a certain distance of it to turn this into clusters, essentially groups of disks that cover all of these different points. The thing that they end up choosing to do is they essentially decide we're going to break this into 8 or 9 groups. And then they essentially find I think they find the smallest balls that cover those points. I use the term balls because I'm used to talking about this in 3-dimensional space where it's spheres, but pardon the phrasing. So they just find, the smallest things. And when you actually look at this very particular image, like what I understand this to be showing is the feature set of the things, and essentially a way to visualize the differences in the features. So when you see these groups, you can kind of see that they do have a lot of overlap, at least within the colors, the individual horizontal rows. So I believe that they're essentially relying on finding some way of doing this where that metric is very small for everything in that group. But otherwise, if you go across groups, it starts getting larger. That's all I have.
I think it's a great answer. And I think to the point, these are very discrete decisions, and obviously they have to go through the papers to define and look for terms and look for things that they can actually categorize with that taxonomy, and then apply this kind of almost 0 and 1 like thing to go over cardinalities. I think of it. I haven't done a lot of this kind of work for many years. When I did more music stuff, music analysis, we could use things like. We would use features for chord detection for kind of trying to find chords in music called chroma, but obviously chords have a relationship between how, where they are between each other. So we also would use that beyond the bag of features, right? You would have some sort of, musical distance that you can actually rely on. But this is obviously coming up with those, to this point, the way they're kind of showing those values. And this is probably the closest you get, this graph right here that groups of problems right here. That's a great question. Yeah.
And that terminology that you're using in terms of bag of features, that means the parameter space of this input set of things that are delineated by this taxonomy looks like a bunch of one-hot distributions, right? Where you have, is that what you mean? In terms of the vector representation, it's got a bunch of, I guess, slots that could be filled. Each one of those slots represents a dimension, and it's either present or not present.
Not present. Yeah. That's what I think that's what Eleanor was getting at as well. Yeah. Now I don't, are there better mechanics for this now looking back in 2023? I think that's an interesting question. So it's hard. I mean, when you're going through these kind of, again, classification, this is very much a classification style paper, and, somebody has to do the work classifying it, or at least determining what are the patterns that derive from all that the history literature they had to go through, right? So that's another question of things. Like, are they missing features? Are they could be like the question, I think, to like rigid, moldable versus rigid, determining some sort of spectrum from that is probably pretty difficult, right? I could imagine.
I wonder if, as we move forward, like one of the cool innovations I think that we're seeing from a lot of these like deep learning techniques is, thinking about that like initial word to vec abstraction of like, if you can swap the contexts of these two things, they must share some vector dimension. They must share a pointing. I think it would be interesting to kind of look at all of these things in the tree and just like shake it a bunch and see which contexts are swappable, as a way to kind of like reduce the dimensionality of the parameter space, and better understand which like of these, I guess, like the subdivision things, like when it suggests that you're going more orthogonal, right? Like each breakdown, I think, of a taxonomy suggests that this is a thing which is less likely to have overlap with other things. Like it's more like you can better represent this as an orthogonal dimension. I wonder if you can get more clues about the relatedness of sub-elements of your tree in a general, like in a taxonomy. It's just like a useful strategy for how to survey these complex, like input parameter space to solution space mapping problems.
Yeah, I think that's an interesting point. I mean, I think the hard part, really probably is like, how do you create the corpus? And by creating the corpus, how do defining that? I think that's actually the hardest part, because though all these terms made sense to me in going through the paper, and it has been things, minus some of the grid computing stuff, which is actually not in my domain at all. I do wonder if I did the same study, would I have come to similar classifications? And then to your point, how do we build more interesting models than that? I think is the key. Yeah, for sure. But I wonder if I would have come, even if I would come up with the same classifications as they did. I think it's pretty interesting, or not. Anyone else kind of on this point? I think this is a really great point that Ace was making, because obviously I'm not so trained in some of the more, and so my circa of really doing a lot more machine learning work was with 2009, like right before, the boom was there a little bit. We were doing a lot of hidden Markov model stuff and kind of hierarchical classification. But I open up to anyone who might think how they might do something like this today, or how they might tackle a problem like this. Or maybe how you would solve the survey of distributed coordination papers as the next gauntlet to go through.
Basically, it's a hard problem, right? Because they had to define kind of measuring dimensions. They had to define criteria, and they say clearly it's, in some cases, the papers don't really address the dimensions we define, so we had to infer it, and sometimes we could, sometimes we couldn't, which is normal, right? If those dimensions are still being identified, of course, not all papers will address them, and so finding the separators that are meaningful. And that way, if you look at the graph with the lines for the 8 categories, it's a kind of parallel plot. It's not that easy to read, right? It's if I were giving this paper has this line, in which of the 8 cluster does this paper fall? Not obvious. And reading the descriptions means that there's actually not that many dimensions that are used to actually discriminate the 8 categories. Actually, I would like a dimension reduction version of this, or principal component analysis, something. But I do get the impression
run PCA on it, right? Yeah.
but I do get the impression that they're not using that many dimensions to discriminate, which makes intuitive sense. You want to have categories that are intuitively obvious, and they kind of recuperated though. But that means that a lot of the dimensions are less clearly necessary. Certainly, if you think about the affinity groups, is it core or a cluster or this or that? This is a fine coarse scale. And how fine do you want to go? How coarse do you want to go? I don't think these are discrete. I don't think the discrete units count as much as how important is it to have fine scale. And there may be more examples like that. It's the one I saw. But.
Yeah, I mean, also, how far back do you go? I think in this one they think 2005. I mean, you also think historically, right? But distributed algorithms we've known has been around for how long, right? And obviously they've applied it more to like what are the kind of categories like this, right? Cloud, cluster, data center, unknown. But yeah, I mean, that's another decision to be made too. Like, when do you do the cutoff? Imagine now, I mean, you'd go from 2015 to 2023. This is probably a different kind of paper, I imagine. And I think, in one of these things as well, I mean, this is again a little bit in Fission's thinking with the stuff we're building. I just gave a talk about some of the stuff we're doing, and a lot of tidbits of the Ambrosia paper we read last time, but also some of these workflow systems like Temporal and Uber's Cadence, and also, from this paper 2015 to 2023, a lot of the scheduling stuff is kind of more and more of it is you just use things off the shelf. You're not typically writing your own scheduler, right? Mostly these other systems have a scheduler attached to them, or maybe some have like pluggable kind of schedulers as well. So it kind of be interesting to see what that is today, right? Like now that maybe there's only a set of, and I guess, in the normal sense, there's only a set of the kind of de facto things that people have used in more recent times with larger companies, kind of, post MapReduce as the only thing. This paper obviously a lot of Hadoopness. Obviously Hadoop is still being used, but was much bigger in this era. And let alone, even though it talks about some decentralization, obviously the things that we think about a lot, Fission, like decentralization, puts a lot of these kind of features together that are like, probably create their own group. Cool. Anyone else with any other things? I had a couple of tidbits that I think are interesting in this paper, like kind of toward the end. This more about things about their criticism. They're calling out of some of these papers. For example, they mentioned some papers do not mention users or customers or clients, and many do not clearly define the context in which the scheduler solution will be used and jobs that are submitted. The other feature that is hardly mentioned is the arrival process of jobs. Although we can infer their values, the feature is usually neglected. And finally, the topology distribution of the solutions is not mentioned in many papers, in which cases we usually consider the solution as not distributed. And, I don't know what to say if that's, we've been doing this group for a year plus. I do think topology distribution is, though there are some papers that tackle it, are pretty, still pretty open and not discussed as much as probably it should be. Multimodal things where you can have a system that can apply to server client versus mesh versus some sort of sub mesh kind of active passive piece. I mean, these are things that somewhat exist commercially, but are not that commonplace. I don't know if people have thoughts on that. But. Yeah, maybe the answer is a future paper reading on topology distribution. Yeah, this is something we talk about efficient because obviously in a decentralized space, you really are dealing with heterogeneity at all levels, heterogeneity of jobs in an open world, but also the heterogeneity of the resources that you can run on home, mobile, large dedicated clusters, things that are low power. So these things all come into play. And you want to expose certain different kinds of workflow mechanics to this stuff. I think that's the main things I had. I thought the Hamming quote in it was really nice. I think that was pretty early as well. I think they have at least a good. I think the motivation in the paper is very nice. For these kinds of things. And again, a lot of people, a lot of researchers won't do this kind of work. You see it really heavy in like HCI, but you do lack it in distributed settings, algorithmic settings. Anything else from anybody else here?
I guess kind of one more like meta question, just because I'm like pretty far away from academia. So like when people write new papers about like, let's say just how to do scheduling, how do they know what papers like they need to cite? Like I'm trying to think about this in terms of like, right, we've got this knowledge frontier of, effectively this like really high dimensional problem of trying to establish good parameter mappings of like inputs to outputs and these like really complex, I guess, like vector spaces. And like when you've got these like large language models, they're trying to like distill that. Currently, I guess it's a lot of like, you've got these groups who are like, hey, we're going to take this subdomain of this problem and we're going to, I guess, like decide the relevant corpus of knowledge that you need to satisfy that you comply with in order for us to accept your paper into this like like this conference. Do you imagine that that's going to like change in the future? Like when you guys read papers and stuff and have to decide, hey, what corpus of knowledge, like what's the feedback cycle of like how often do you create these survey papers and like where does the general body of knowledge exist and how do you know what the body of knowledge that committee needs to be responsible for maintaining is? Sorry if that's super abstract, but I'm just kind of really curious about all this stuff.
I can answer. I mean, I'll give my answer as having just written a paper that I went to a conference last year, trying to write a second one. The more PL programming languages, which are probably a little bit more like a homogeneous kind of crowd, where you better put the right references, or you'll get criticized very heavily. So I mean, well, to your one question about survey work is lacking, and that's and it's sad. Like you actually, so like, at least in, I can speak only from a little bit at U.S. institutions. Like they'll not always publish. A lot of first or second years are asked to kind of do surveys about the work they're going to do as like either with their group or maybe something for like a tied to a class, but not at the publishing material that you would get at something like the computing surveys one. And there's always a lot of papers at conferences that are doing something a little bit new, but really have great historical connection, and those typically, if it's still not novel enough, the historical collection is not that important. It only has to come with whatever that feature of novelty is, which is problematic, right, in so many scenarios. But I would say, like having for the work I do and kind of type theory work, a lot of it is my advisor knowing, like, I think that's part of like a good professor. I mess up names all the time. He's always correcting me on all his names and his opinions on certain papers, for example. So that's one. I think there is a tree of knowledge that comes from people who worked in this historically for a while. And also a lot of even younger professors and stuff, like you have to read, part of your job as a professor on a tenure track, typically, again, is to be on committees, reading papers, judging them superficially or not, and then therefore you have kind of backing from being on those committees and reading all those papers, even though, including the ones that didn't get in. Additionally, at least in again, programming language circles, if you write a paper and even if you're partially going to get accepted, your review feedback will include, why don't you cite these 14 papers? I wrote 8 of them, but you don't know who I am because I'm anonymous. That will happen. And then you end up just citing those papers. But typically, I think it's like, part of good work, in academic thinking is I'm working on this kind of thing, and maybe I was influenced by something in industry, maybe not. But then, the deep dive is spending a lot of time with Google Scholar and these kind of things, picking one thing as part of your work, and then diving into those citations until you hit some leaf that you're like, okay, I think I covered the span. And obviously some of this stuff is rediscovered later or reinterpreted better later, and you can reference that and maybe, but you still like to reference like the original OG thing, as well. So at least I think that's the way, but the problem is there's not a lot of survey work that's being kind of publicized, because as a researcher, there's not a lot of, really a couple known conferences in the field. You're meant to do novel work, not reinterpret or rediscover work from others. I
Interesting.
don't know if that's helpful.
Yeah, thanks for, I guess, hopping into that. It almost
It will be a little different from different subject matter. Systems will work a little differently than other ones too, but go for it.
No, I was just saying it seems really similar to like a lot of distributed consensus problems where you've got these kind of like actors in a committee and we're holding this state space of what principal components of things that they need to care about, and you're just trying to create general acceptance to accept this thing into this like public knowledge space, which I think is a really fascinating way to think about the problem. And it's just like ever expanding circles of consensus that you need to have and build in order to accrete knowledge into this kind of like I don't know, collective loose mapping of I don't know, sorry, I'm being super hand wavy, but
no, it's actually correct. I mean, there are no right answers here. I'm not in the particularly NLP or machine learning things. That stuff tends to be like a more incremental, especially if you're trying to get numbers. You're trying to showcase that you have better performance on a certain model. You really will look at the last set of material. And those conferences are like, the amount of papers are huge, and like they're very there's just constantly like a bunch of papers like in that field. If you're a machine learning researcher, particularly applied, less on the theoretical side, but on the applied side, you got to have a ton of papers, or you're doing like social graph stuff or whatever the case might be. In programming languages, you're hitting like 5, and systems, a little bit like that as well. Those systems tend to have the big group things. So even though you might have 2 or 3 first author papers, you also own like a bunch of other group papers. And the whole thing with the first author stuff, which is such a BS, I guess I can say. The great paper by the Domains. They're these great people at MIT, and it's called it's this paper about first authors, where it's like how to make it where first authors and like how to it's like kind of a comedy paper, but it actually gives you like a LaTeX template to get rid of the whole first author approach to things. I'll have to link that. It's very, very good. Very academic, funny. But yeah, it's it is sad that things like surveys are. I've lamented it for a while because I probably would have been really happy just like doing it. It's like historical computer science work. Typically now the people who do there's a great talk given at a couple conferences by guy. How do I forget his last name now? Terrible of me. Yeah, I'm gonna look it up. So I'm gonna feel bad. Yeah, I'll come back to me in a second. But Guy Steele, yeah, of course, Guy Steele. About again, he did this on his own because he's like super tenured, been at, I guess, Oracle, Microsoft, or whatever for like forever. So he could do whatever he wants. And he gave a great talk about the history of language semantics in programming languages and how people use, what symbols they use, right? What Greek notation they use and how they misuse it or like change it again. That there's even papers that have little appendices about we're using these symbols that are related to this, these other versions, the same symbol somewhere else, but a little bit different. And so it's a really great talk about kind of the history of that. And again, I love those kinds of like computer science history and bring it to the modern century kind of stuff. And surveys are kind of like that, but sadly they're not as popular as they should be. But you're correct. It's really a big mess of actors in the state space, and they're all trying to communicate. Yeah. So cool. We're at time. Really great stuff today. I know I gained a lot of it. Really awesome. Our next paper, which I have up here. I think the next session will be on July 3rd, and it's a paper that won one of the best papers at SOCC 2022. This goes really into big company research, how to fight production incidents, an empirical study on a large scale cloud service. So I think I've heard really great things about this paper. I have not read it yet, but this should be pretty fun to get some really large problems. And actually, this is kind of interesting retrospective kind of work, looking at major issues. So should be pretty fun. Anyone, any other concluding thoughts before we head out? All right, cool. Well,
Thank you
thank you very much
for running this. This was been
Thank
awesome,
you.
and it's always an enjoyable
Thank you for the
part of
great
my month.
questions. Yeah, and thank you, Eleanor, for the awesome intro to this paper. That was awesome, and all the answers. So we'll see you in July.